The Earth is basically a great big capacitor. The ground carries a negative charge. Then there's the insulator, which is the air, and the top layer carries basically a positive charge. And between the two, there is a mysterious force present in every corner of the world. A force so quiet and so constant that most people never notice it. It drifts in the air, cities, forests, oceans, and mountains. It surrounds every person without ever drawing attention to itself. Yet, this force is real, measurable, and surprisingly powerful. It is the natural electric field of the atmosphere. And even though it has been part of Earth's environment for as long as the planet has existed, most people have never considered the idea that it can be harnessed. When someone first hears that atmospheric electricity can be used to produce power, they often jump to one of two reactions. One person might smile in excitement and claim they always suspected that free energy was hiding in plain sight. Free energy, Jay? There is no free energy. And that power companies have been taking advantage of them for years. Another person might laugh and assume the speaker has finally gone too far, drifting into the realm of fantasy. But the truth is, atmospheric electricity is not mythical or imaginary. It is a genuine physical phenomenon. It was discussed earlier in video 1840, and the explanation still stands strong today. The Earth behaves like a gigantic ball loaded with electrons. The sky above it contains a layer of positive ions. Between these two regions lies a continuous, natural voltage gradient. Every meter someone moves upward adds roughly 100 volts of potential difference. The air may feel empty, but it is full. If a person rises far enough up, toward 52 kilometers, the potential difference reaches hundreds of thousands of kilovolts. Scientists have measured this effect since the early 1900s. Balloons, towers, and aircraft have all confirmed the existence of the atmospheric field. Lightning itself is the most dramatic evidence. It is the natural discharge of the very field that surrounds us. This entire phenomenon belongs to the study of electrostatics. Electrostatics deals with charges that do not move rapidly, unlike the electric currents that travel through power lines. One way to picture it is as the magnetic behavior of electric charge. The rules are simple. Charges that are alike push away from one another, while charges that are opposite pull together. These rules create countless small effects in everyday life. A plastic rod rubbed with a cloth can pick up paper scraps. A doorknob might shock someone on a dry day. Even the dust pattern on old screens comes from electrostatics. For many years, people believed electrostatic forces were too weak to be useful. Early electrostatic machines were viewed as toys. There were small motors made from styrofoam cups, aluminum tape, and foil discs. They spun gently when charged, but few took them seriously. The challenge was simple. Low voltage meant low force. But modern knowledge shows that high voltage can be generated safely, and high voltage produces a strong electrostatic push. High voltage does not automatically mean high danger if the current remains extremely small. A device can hold thousands of volts and microamps at the same time. The voltage gives the push. The microamps make it safe. With this understanding, the new atmospheric motor was created. Its design is intentionally simple. It uses 5 main parts: the drum rotor, 2 end plates, 4 bars, 12 threaded rods, and 24 thumb screws. Most of the machine is plastic because plastic holds charge without leaking it. Metal surfaces leak charge too quickly, reducing efficiency. The drum is the rotating element. The end plates support the drum with skateboard bearings. The bars hold the rods. The rods hold the combs made of long nails. Each part contributes to forming the electric field pattern needed to create rotation. The creator of the motor openly states that all ideas released are public domain. Anyone can build the machine, modify it, or use it as a starting point. The goal is to encourage curiosity and experimentation. This openness is also practical because the machine does not require specialized tools. A basic 3D printer, some bolts, copper tape, and nails are enough. Construction begins by printing 12 rods with threads on both ends and holes along the length. 1 centimeter copper tape is applied to each rod. Copper tape is ideal because it is flat, flexible, easy to press into place, and highly conductive. It forms the electrical backbone of each comb. Next, 30 centimeters nails. Thin pins 1.5 millimeters in diameter are pushed into the holes. The pressure of the nails against the copper makes a good connection. Measured with a meter, the resistance between the tape and the nails is around 0.2 ohms. This is a strong connection without solder. The rods are secured with M425 bolts. 12 combs are built this way, forming a ring of evenly spaced electrodes. The drum rotor is constructed by inserting an 8 mm metal bar through its center. The outside of the drum is wrapped in aluminum foil used for HVAC ducts. This foil is smooth, conductive, and lightweight. Once the foil is wrapped tightly and pressed to remove wrinkles, it forms a uniform conductive surface. The end plates each hold a skateboard bearing. These bearings let the drums spin freely with minimal friction. threaded rods attach the two plates and hold the entire frame. Before tightening, the combs are installed. They alternate in polarity. One red comb pointing its nails in one direction, then one black comb pointing its nails in the opposite direction, and so on. This alternating pattern builds a balanced electric structure around the rotor. After installation, all red combs are connected with cables and 4 mm crimps. All black combs are connected the same way. Two terminals are formed, a positive side and a negative side. Now the motor is ready for testing. Testing requires a ground and a static charge source. A Van de Graaff raft generator works. A plastic sheet rubbed with wool works. Even a wire thrown upwards in mid-air can collect natural atmospheric charge. But the first test uses a high voltage supply because it allows precise control. When only a tiny high voltage input is applied, enough to show about 2 volts in the final output, the rotor begins to move. The current is in the microamp range. A small push, but enough to show life. Increasing the voltage to around 2.5 kVds causes the motor to spin faster. Higher voltage increases speed dramatically. The rotation becomes smooth and impressive. People often underestimate electrostatic machines, but modern developments show their potential. Independent creators like Laser Hacker demonstrated atmospheric motors such as the Atmia, showing how charge from the sky can drive a rotor. Industrial projects like the C motor explore these concepts on larger scales. The scientific foundation goes back to researchers like Oleg Jefimino, who wrote extensively on how electric fields themselves can act as sources of mechanical energy. This particular motor uses nails not only because they are simple, but also because they solve a problem. Some earlier designs placed electrodes so close that they nearly touch the rotor. When the voltage rises, air breaks down at about 1000 volts per millimeter. Sparks jump at small gaps. Sparks waste energy and can damage the machine. By spacing the nails at a safe distance, this design avoids arcing. Instead, the motor uses induction. The positive charge in the air pushes the negative charge onto the drum surface. The drum rotates because the electric field is constantly trying to shift charges as the foil passes the combs. One of the coolest aspects of this design is its accessibility. Most of it can be printed. The metal parts can be bought at any hardware store. No soldering is required. No complex tools are needed. Anyone with curiosity and patience can build it. During early tests, parts like the handles and feet caused snags. These were removed. Future versions will fix such issues. But even at this early stage, the machine performs impressively. Atmospheric electricity is a force that has been around forever, yet barely explored in daily life. It moves quietly between the ground and the sky, interacting with clouds, storms, and even solar winds. For decades, people believed it was too diffuse to use. But modern tools, high-voltage knowledge, and better materials show that it can indeed be tapped. This motor is one example. It shows that a simple, well-arranged set of rods and foil can turn invisible charge into real physical motion. And the quiet spinning of the drum suggests something larger. That clean and natural energy might be hiding in places most people never expect. As research continues, future versions of this motor may include better spacing, tuned blade shapes, improved electrodes, and automatic collectors that pull electricity straight from the air. Some designs might use taller frames that capture stronger potential differences. Others may adopt new dielectric materials to reduce leakage. Even with simple materials, the possibilities are wide. For now, this machine stands as a working demonstration of a natural force that surrounds everyone every day. With curiosity, patience, and a few basic tools, anyone can explore it. The sky above us holds more electricity than we ever imagined. And this motor is proof that the invisible field can come alive. Thank you so much for watching all the way to the end. If you enjoyed this deep dive, please smash that like button. Share your thoughts in the comments below. And don't forget to subscribe and turn on notifications so you'll never miss a future update. We've got a lot more exciting tech stories coming your way. Until next time, stay curious, stay inspired, and we'll see you in the next video. Goodbye.